Hello and welcome. Today we'll be diving into an essential topic in chemical kinetics, reaction rate and rate laws. We'll learn what they mean, how they're calculated, and how they apply in real world examples. By the end, you'll have a clear understanding of how reactions speed up or slow down and how scientists quantify that. What is the rate of reaction? The rate of reaction tells us how fast or slow a chemical reaction happens. It measures how quickly the reactants are used up or how quickly the products are formed. How to understand it? Imagine you're filling a glass of water from a faucet. If the water is flowing fast, the glass fills up quickly. But if the water is dripping slowly, it takes much longer to fill the glass. The rate of reaction works in a similar way. It's like measuring how fast the water, or in this case the products, fills up. Formula for reaction rate. The rate of reaction is usually expressed as rate change in concentration per unit change in time. As the reaction proceeds, the concentration of reactants decreases. That is, they're getting used up. The concentration of products increases as more are formed over time. Let us take the example of the reaction between magnesium and hydrochloric acid. Let's say you drop a piece of magnesium metal into a solution of hydrochloric acid. They react to produce magnesium chloride and hydrogen gas. If you use a strong acid or warm the solution, hydrogen gas bubbles out quickly, meaning the reaction has a fast rate, and if you use cold acid, the hydrogen bubbles form slowly, showing a slower rate of reaction. Now let's study what affects the reaction rate. Here are some factors that influence the reaction rate. First is concentration. More reactant molecules mean more collisions, which can make the reaction faster. Second is temperature. Higher temperatures give molecules more energy, making them collide more often and react faster. Third is surface area. Breaking a solid reactant into smaller pieces exposes more surface area, allowing the reaction to happen more quickly. And last is catalysts. These substances speed up a reaction without being consumed by it. In simple words, think of the rate of reaction like a race. The faster the reaction, the quicker the finish line is reached. That is, the products form. If there are more runners, that is higher concentration. Or if the runners have more energy, that is higher temperature, the race is finished faster. If the runners are slow, that is low concentration or temperature, the race takes longer. Now, let's talk about rate laws. A rate law tells us how the concentration of reactants affects the reaction rate. What is rate law? The rate law is a mathematical equation that shows how the rate of a chemical reaction depends on the concentration of the reactants. It tells us which reactants affect the speed of the reaction and how their concentrations influence the rate. How to understand it? Imagine you're baking a cake. The time it takes to bake depends on the temperature of the oven and the ingredients. If you double the oven temperature, the cake bakes faster. In a chemical reaction, the rate law shows how changing the amount of certain ingredients, that is reactants, changes the speed of the reaction. The general form of the rate law is given by rate is equal to Ka raised to m b raised to n. Let us take an example of reaction. A moles of A plus B moles of B plus C moles of C gives R moles of R plus S moles of S plus P moles of P. We can write rate law expression as minus RA is equal to KCA raised to alpha, CB raised to beta, CC raised to gamma, where N is equal to alpha plus beta plus gamma, and N represents order of reaction. Alpha, beta, and gamma represents the individual order of reaction with respect to reactant A, B, and C respectively. K represents rate constant. Reaction can be classified based on the order of the reaction. Zero order reactions. In a zero order reaction, the rate of the reaction does not depend on the concentration of the reactant. No matter how much of the reactant is present, the reaction will proceed at the same rate. How it works. Think of it like baking cookies in the oven. If you have 10 or 100 cookies, they will bake in the same amount of time because the rate, that is oven heat, doesn't change with more cookies. Example of zero order reaction is decomposition of ammonia on a platinum surface. First order reactions. In a first order reaction, the rate of the reaction is directly proportional to the concentration of one reactant. If you double the concentration of that reactant, the rate also doubles. How it works? Imagine a cup of hot coffee cooling down. The hotter it is, the faster it cools. As the temperature decreases, the cooling rate slows down. It's a bit like the speed of reaction adjusting with how much reactant you have. Example of first order reaction is radioactive decay. Last is second order reaction. Let us understand it with a simple example. Think of a group project where each person needs a partner to get their task done. If there are only a few people, it takes longer for everyone to find a partner and start working. But if you double or triple the number of people, they can quickly find a partner and complete the project faster. In a second order reaction, each person represents a reactant molecule. When you increase the number of people, that is concentration of reactants, there's a greater chance for them to pair up and work together. That is, to react, which speeds up the reaction. In a second order reaction, the rate depends on either the concentration of two reactants or the square of one reactant. If you double the concentration of the reactant, the rate increases 4 times. Summary. Let's recap. The reaction rate tells us how fast a reaction proceeds, and rate laws describe how reactant concentrations affect that rate. Different reactions follow different orders, and the key to finding the rate law lies in experimentation. Thanks for watching.